Hi everyone, thanks for coming. I'm Daming Zhou from ETH Zurich. Today I'm glad to be here to present our recent work, Oracle free repair synthesis for floating point programs. So let's start. Before the detailed introduction, I would like to highlight the keyword of this work. We know that to repair floating point error, a ground truth or Oracle implementation is indispensable in existing work, which is a very challenging and expensive prerequisite in practice. So the keyword for this work is Oracle free. Our tool Acesso doesn't need Oracle at all, which makes it much more practical. At the same time, Acesso is also both effective and fast, that can reduce floating point errors by orders of magnitude under 1 second. Here is the outline of this talk. The first part is about the background. The second part is about difficulties when using even the state-of-the-art techniques. The third part is our approach Acesso, and the last part is the evaluation of Acesso. In the first section, let's start with floating point errors and how existing approaches repair them. Since floating point use limited precision to represent unlimited real numbers, there are always floating point errors, and existing error detection work could report us an erroneous input interval where the errors become significant. Considering this tiny example, we know that library calls are widely existed in numerical programs. So in this particular example, we call an GSL's Basel function here. We notice that when the input is 1.2 times 10 to the minus 5, the result of our function foo triggers significant floating point error. There are 6 invalid digits for a double precision number. We also provide the oracle here for reference. In later part, we will use this example to motivate and illustrate our work. To repair floating point errors, we can formulate the problem into this. Given a floating point program f hat and an erroneous interval I based on error detection technique, our goal is to generate a patch that compute accurate result on I. For existing approaches, they heavily depend on Oracle implementation F to guide the patch synthesis. For the sample inputs with interest, they calculate the Oracle output on each of them and use such result to construct the patch. A patch is usually an alternative computation of the original program, for example, a polynomial or a mathematical equivalent. However, implementing an oracle is generally very challenging, which we will discuss next. In this section, we will discuss why oracles are generally hard to obtain in practice. To obtain oracles for numerical programs, an intuitive idea is to replace all floating point types for higher precision, for example, from double to long double or even higher. At this level, replacing types is not hard, and we do have MPFR library that provides high precision types. However, high precision types do not guarantee high precision results, or we say high quality oracle, because an oracle requires all operations, not just the types, to have higher precision. Library calls and precision-related operations prevent us from getting oracle easily. So what is precision-related operations? Precision-related operations are hard-coded series and hard-coded iterations, which widely exist in numerical libraries. It's typical for numerical scientists using Taylor series to calculate functions. For example, series for sin x when x near 0. Here is a program that corresponds to the series. We notice that the program only calculates the first 4 terms of this series because x is quite small. So the error term OX to 8 can be neglected for double precision program. However, for this kind of program, using higher precision types cannot make the result more accurate, since we need to manually add more terms of the series. Back to our example, which involves a GSL Basel function. It also contains hard-coded series inside. For the application developers that simply invokes the library, they are unable and unwilling to deal the hard-coded magic numbers and to re-implement each of the library call. At the same time, we cannot expect MPFR library to support every library call either, So seems we are in a dilemma here. And the question is whether it is possible to repair floating point program without an oracle. In past years, there are some oracle-free detection work that could feed us the erroneous input interval. And besides, the only information we can get is some erroneous outputs. This question will lead to our approach next. In the third part, we're going to introduce the concept of microstructure for floating point arrows and introduce our approach as SESO based on microstructure. Here comes the key insight of our work, the microstructure of floating point arrows. For a given program and a given input, we notice that microstructure shows up under a certain neighborhood. The figure here shows different neighborhoods for the same input. In each subfigure, the x-axis is the input under different neighborhood, and y-axis is the floating point result and oracle result, just for reference. In this figure, from left to right, we zoom in like a microscope, and the neighborhood becomes smaller and smaller. We notice that there do exist microstructures that caused by floating point arrows. In the fifth one, the microstructure is significant. It clearly repeats 3 times. And in the first one, the neighborhood is larger and it repeats more times. The key idea is, if we can find a neighborhood with significant and complete microstructure, it is possible to infer and estimate the oracle just using the floating point result, like in the third one and the first one. Next, let's look at more cases. To use a neighborhood for estimating an oracle, a suitable one should satisfy 2 basic principles. On the left hand, the value change inside the neighborhood mostly comes from the function itself, but not the floating point arrows. So the microstructures are insignificant in this column. Since we want to observe the floating point arrows rather than the function values themselves, the microstructure should be significant. On the right hand, microstructures are incomplete and thus biased, which will further lead to biased estimation. So these are not ideal neighborhood either. Thus, on the middle columns, the microstructures are both significant and complete, where estimating the oracle becomes possible. Actually, we propose a formula to formulate the neighborhood selection process. With the selected neighborhood, we can simply sample inside the neighborhood to estimate the expected value and the error variance, which are both useful in our later steps. We also highlight that the entire process is oracle-free and can provide accurate and relevant information. In our example, the estimated expected value improves the accuracy by 2 orders of magnitude, and the estimated error variance is also accurate. Previously, we discussed how to observe microstructures and obtain information on arbitrary inputs. Now we use an animation to show how our approach as SESO repairs the entire erroneous interval I. First, we sample a set of inputs in I. Next, on each sample input, we collect its microstructure and estimate the expected value y and error variance. And finally, we generate a polynomial based on all y and variance information. Actually, we will also validate the patches based on microstructure, but due to the time constraint, we skip the details here. In our motivation example, a simplified patch will look like this. In the erroneous input domain, from negative 0.01 to positive 0.01, we use the synthesized polynomial to provide more accurate results. And the other input domain, the program still invokes the original program. So we review the entire process for a SESO to repair a program. First, we sample inputs in the given erroneous interval I. Second, on each sample input, we use our formulated method to select neighborhood where the microstructure is both significant and complete. Third, on each sample input, we estimate the statistical information y and variance under the selected neighborhood. And fourth, we generate and validate the patch based on all statistical information. In the last section, we introduced the evaluation on SSO and answer 3 questions. How effective is SSO? How microstructure contributes to SSO? And how fast and scalable is SSO? The benchmark of our evaluation includes 36 commonly used univariate functions, where 17 of them involves library calls, whose oracles are very hard to obtain and thus cannot be handled by previous work. 15 functions are directly from related work, and we also include 4 error-free functions as a control group. On error-free functions, we know that there won't be available patch, but we're still curious about how SSO deals with them. In the first part of our evaluation, we focus on how SSO could improve the accuracy on both maximum error and average error. The figure on the right-hand side shows that patches synthesized and validated by SSO are all superior to the original programs, where floating point errors are reduced by orders of magnitude. On the control group, we know that there won't exist a better patch. SSO doesn't have such information, but it still correctly reports patch unavailable after the patch validation step. This result confirms that SSO is highly effective. Empirically, it reports superior and only superior patches with confidence. In the second part, we assume we don't have microstructure, and we use pure floating point result to do the polynomial synthesis. We can see clearly that the patches become less accurate than the last part, and numerous patches become even inferior than the original program. We conclude that microstructure is critical for SSO's effectiveness. Otherwise, we will have to report inferior patches to the users. Since in practical scenario, it's very hard for developers to distinguish the quality of a patch. Inferior patches will greatly reduce the practical value of an approach. The third part of our evaluation is regarding scalability. On average, SSO costs under 1 second to generate a patch, which is super fast. The generated patches are also highly efficient. On average, an execution of SSO's generated patch costs only 9 nanoseconds, which is even faster than the original program, which costs 36 nanoseconds on average. Since the patches are polynomial with fixed terms, they are with constant performance. In other words, the patches are always this fast. In this final slide, we conclude several takeaways for this talk. First, we propose the SSO, which is an effective and fast technique for repairing floating point errors. Second, we discovered that floating point errors have microstructures, which reveal rich information on the floating point errors. Leveraging microstructure brings several advantages. Most importantly, it is oracle-free, and we can estimate values and error variance based on microstructure. It is also helpful in terms of validating results. We also expect the findings in this paper to provide insight for future applications, such as detecting floating point errors and debugging floating point programs. That's all. Thank you for your attention.